The Logic of Persistence. Abstract. This book develops the case that the 288 physical constants of nature are necessary consequences of geometry, structural aspects of the simplest non-trivial hyperbolic three-manifold, the hyperbolic figure-8 knot. By uncovering 2 structural rules and 5 modular boundaries, the Planck constants, we reveal that the constants of nature emerge as coherent outputs of a single geometric system. What begins as a catalog of Kodata's empirical values becomes a unified grammar of physical persistence, deeply grounded in symmetry, invariance, and the logic of manifolds. This work offers not only a framework for understanding physical law, but a structural ontology that reshapes how we interpret the connection between measurement and meaning. Chapter 1. Ascending the Footholds of Awareness. Consciousness fits us to our environment. To become more conscious is to come into possession of an awareness of your environment that better fits you to it. The more accurately you understand your environment, the more you can do in it. That is, as our consciousness evolves into a more faithful mirror of reality, as we cognitively grow up, the powers available to us increase. For a long time, understanding the world was a matter of best inference, a thing often deferred to whichever authority was most beneficial to believe in. What we believed about the world was shaped not only by truth-seeking, but by how those beliefs isolated us or united us with others, and how that grouping provided us security. For early humans, the world was experienced through the mythological lens that best fit each individual to a network that supported its survival. This response is a natural consequence of fitting yourself to a world that provides very little security. Because of the narrative our early ancestors had for what reality is, they were aware of only a small fraction of the resources actually around them. For example, they didn't see electricity as an available or controllable element of the world. The electron just wasn't a thing they had noticed. As a result, the range of what they had access to or could affect in a world constructed from electrons was significantly restricted. What engageably exists is framed by the limit of each person's exploration and the story they tell themselves to make sense of it all. Whether that worldview has been handed to them by other parties or forged by the footholds of personal discovery, every person is bound by the limits of their own lens on reality. Every element of the real world that our story doesn't capture restricts our ability to interact with it through that element. The ultimate quest of science is to align our consciousness with the true story of what reality is. This is the goal because accomplishing it would mean having access to all the powers of nature. Having the true story of reality would enable us to transform into beings that are able to see all the real degrees of freedom in front of us, and to understand how to use them. With this understanding, we would find ourselves in a world full of more energy than we could ever need, freely available, always there. To achieve that goal, we must possess the story that gives structure to all the intrinsic elements of reality, the elusive theory of everything. Thinking through the lens of such a story would elevate us into the kind of creature whose intelligence has matured beyond the need for money or the hoarding of resources. Having both an understanding of how each power is granted into the world and how to use them means we could convert mass to energy, or other forms of mass. We could make water from the nitrogen in the air, making it freely accessible anywhere in the world. We could grow the perfect tomato as reliably as executing a computer program. We could finally outgrow the mindset of scarcity. Chapter 2. Overview of the Search for a Theory of Everything. Humanity's attempts to see the truth about reality took a historic leap when Anaximander, approximately 580 BCE, became the first person in recorded history to look into the world and then systematically test if what he thought he was seeing was correct. Somehow, he became aware that he was telling himself a story about reality, and with this awareness, he became interested in what the true story was. So interested, in fact, that he became the first person to get to know his environment by coherently measuring its features, bringing time and space into logical unity, into a single language. He invented the gnomon, a rudimentary but revolutionary sundial for systematically measuring amounts of time, connecting measures of time to measures of distance. And he invented one of the first maps of the known world, with scale, proportion, and orientation, paving the way for cartography, geometry, and physics. While others explain the world through divine agencies or anthropomorphic forces, Anaximander saw the world as bound by a principle of balanced opposites. Hot and cold, dry and wet, motion and rest. These were all different expressions of the balance built into the world. For centuries after him, however, it would be Aristotle's teleological framework that dominated, a view in which objects moved not by rule, but by purpose, seeking their natural place in a cosmic hierarchy. Anaximander framed the cosmos as a dynamic system governed not by gods, but by principles, in which change was lawful and where justice preserved balance between opposites. This gave him access to a model of nature that was ordered and intelligible. In contrast to mythological worldviews, his ontology provided a structural foundation for systematic inquiry. This was the first seed of thinking that the universe could be known, not through stories of divine will, but through its own inner logic. But the idea that the world could be systematically tested, probed not just by principles, but by quantifiable experiment, would have to wait for centuries to come into full bloom. Then came Galileo. Galileo had the revolutionary insight to ask not only what gravity was, but how it behaved. Instead of being passively mystified by gravity, he had realized that he could actively engage with this mystery and see further into it by measuring its action. By systematically tracking the fall of bodies and timing their descent, Galileo uncovered a profound pattern. The distance an object falls is proportional to the square of the elapsed time. After 2 seconds, a falling object does not simply fall twice as far, it falls 4 times as far. After 3 seconds, 9 times as far. Even more astonishing, if you broke time into equal increments, say 1 second each, the distances covered during each successive interval followed the sequence of odd numbers, first 1 unit, then 3, then 5, then 7, and so on. It was as if nature herself was quietly performing mathematics, generating sequences of squares and odds beneath the visible motion of falling objects. Galileo revealed that nature's unfolding was structured by mathematical symmetry, a symmetry between time and distance, between counting and motion. Gravity expressed an underlying relation, a silent agreement between duration and change. In the logic of falling bodies, Galileo found a harmony that binds motion to measure via the mathematical music of symmetry. Galileo's discovery was not simply that motion could be measured, it was that different aspects of motion, distance, time, and velocity, could be locked together into a coherent structure. And moving beyond Aristotelian intuition, Galileo began to uncover an invisible framework, one where measurements were not isolated, but interwoven by logical necessity. This was the first clear glimpse of a principle that would later become indispensable: coherence. If units of distance and time had floated freely, logically disconnected, acceleration itself could not have been defined. The grammar of physics would have fractured. Galileo's quiet revolution was not only to mathematize motion, but to reveal that motion's measurements were coherently interdependent. In the moment of that discovery, the world changed. Law replaced will. Pattern replaced purpose. Galileo had realized that to know the universe was not to interpret its intentions, but to measure its relations. In his own words, he wrote, "Philosophy is written in this grand book, the universe, which stands continually open to our gaze. But it cannot be understood unless one first learns to comprehend the language and interpret the characters in which it is written. It is written in the language of mathematics, and its characters are triangles, circles, and other geometrical figures, without which it is humanly impossible to understand a single word of it. Without these, one wanders about in a dark labyrinth." A central insight of Galileo's work, the principle of Galilean relativity, was to see the laws of motion as the same in all inertial frames, all reference frames moving at constant velocity relative to one another. Shut yourself up with some friend in the main cabin below decks in some large ship, and have with you these same flies, butterflies, and other small flying animals. Have a large bowl of water with some fish in it. Hang up a bottle that empties drop by drop into a wide vessel beneath it. With the ship standing still, observe carefully how the little animals fly, with equal speeds to all sides of the cabin, and, in throwing something to your friend, you need throw it no more strongly in some direction than another, the distances being equal. Jumping with your feet, you pass equal spaces in every direction. When you have obtained all these things carefully, have the ship proceed with any speed you like, so long as the motion is uniform and not fluctuating this way and that. You will discover not the least change in all the effects named, nor could you tell from any of them whether the ship was moving or standing still. Galileo Galilei. These facts about the world imply that there is no privileged reference frame in the universe. Galileo found that motion is relative, but the laws of physics are universal. This shattered Aristotelian notions of absolute rest and provided a conceptual bridge to Einstein's later work on special relativity. Galilean relativity revealed a profound symmetry built into the world. Not only could the world be measured, it could be measured from anywhere and still yield the same truth. The world was not centered around one vantage point, but expressed its laws through invariant relationships, revealing an underlying harmony that transcended particular perspectives. This was more than a technical insight. It was a philosophical revelation that nature, at its core, is structured to be intelligible from within itself through shared, unchanging principles. These invariances would later be recognized as expressions of deeper symmetries in the fabric of physical law. Galileo believed that the universe was written in the language of geometry. To know the world, one had to learn to read this language. Rather than appealing to final causes or intrinsic purposes, as was common in Aristotelian thought, Galileo focused on quantifiable properties, extension, duration, speed, mass, temperature, and so on. He brought into being a worldview where nature could be described by universal laws discernible through observation and experiment. His approach was not merely mechanistic, but structural. Beneath the visible lay a lawful, relational architecture that could be revealed through precise inquiry. This was a pivotal shift. In Galileo's view, to know something was not to ask why it existed in terms of meaning or divine intention, but to ask how it behaved in terms of rule and relation. His ontology was dynamic, intelligible, and reproducible. It laid the groundwork for the belief that every feature of the natural world, no matter how mysterious, could eventually be brought into the clarity of measure and law. Then came Kepler. While Galileo unveiled the secret patterns of falling bodies, Johannes Kepler was piecing together the hidden grammar of the heavens. Armed with Tycho Brahe's decades of meticulous observations, Kepler did something radical. He treated the data as a text to be deciphered, not merely recorded. He searched for patterns, and he found them. Planets traced ellipses, not circles. They swept out equal areas in equal times. Their periods squared were proportional to their distances cubed. 3 simple laws, distilled from countless nights of observation. Kepler did not know why these laws held. He did not know what forces bent planets into ellipses, matched area to time, or squarely connected periods to cubic distances. He simply saw that the patterns were there, the hidden music of the cosmos. If Kepler had not done this, if he had not wrestled data into law, Newton would have had no structure to explain. Kepler gave the world a grammar of planetary motion. Newton would give it syntax. Then came Newton. With Galileo, the world became measurable. With Kepler, it became lawfully patterned. With Newton, it became predictive. Newton's ontology marked a radical deepening of Galileo's structural worldview. He saw the universe as a coherent and self-consistent system governed by inviolable mathematical laws, laws that could be expressed in universal terms and applied to everything, from the fall of an apple to the orbit of planets. Space and time, in Newton's view, were absolute arenas within which events unfolded with perfect regularity. The cosmos was not a domain of capricious forces or invisible intentions. It was a grand clockwork of motion and force, governed by predictable relationships. Newton immersed himself in the world, not just observing it, but extracting its principles with relentless curiosity. He dissected the colors of the rainbow, described the properties of fluorescence, and investigated the behavior of light and optics with profound precision. His contributions were not isolated flashes of genius. They were part of a consistent effort to unravel the fundamental rules of nature. Each investigation was grounded in the assumption that nature's behavior was not arbitrary, but rooted in universal order, a conviction that the world's complexity was governed by intelligible mathematical simplicity. Newton's exploration of the world was greatly enhanced by his fascination with discovering the rules for how things work. By meticulously examining the structure of combinatorics, he discovered the rules of calculus, the mathematics of change and accumulation. Newton formally achieved his advanced vision of the world, capable of tracking and explaining far more features than any model before, by creating this new mathematical language. Calculus makes it possible to describe not only static structures, but dynamic systems, objects in motion, quantities in flux, rates of change. With it, the changing position of a falling object could be tracked through velocity and acceleration. The bending of light, the flow of heat, the growth of populations, all become accessible to analysis. Calculus provided the grammar for the new story of reality, one in which change itself was no longer opaque, but governed by smooth, discernible curves. This new mathematical framework was not just a technical achievement. It was a crystallization of Newton's ontology, a universe governed by precise, lawful transitions from one state to the next, where even the forces behind the fall of an apple or the orbit of the moon could be resolved into universal principles. Calculus revealed a world where movement and causation were no longer mysterious flows, but measurable, predictable arcs in a mathematically coherent structure. The clarity of Newton's ontology was transformative. He shifted the question from what happens to by what rule does it happen? His view of the world was one of elegant inevitability. Everything that moves, moves according to law. And that law was written into the very equations that would define centuries of scientific thought. Before Einstein could frame gravity in terms of geometry, Bernhard Riemann had to first give us the language in which such a geometry could be described. Riemann extended the Newtonian tradition by asking, how can we characterize the shape of a space in which calculus still works? In response, he developed the concept of a manifold, a structure that may curve and twist in higher dimensions, but retains local Euclidean behavior. Far from being a mere mathematical abstraction, this was a conceptual revolution. Riemann introduced a way of thinking about geometry as dynamic and intrinsic, no longer dependent on embedding in a higher flat space, but described entirely from within. Crucially, Riemann showed how curvature could be quantified using a metric, a rule for measuring distances within the manifold, and how this metric could vary from point to point. This gave rise to the very idea that space could have internal structure. His work planted the seeds of a new kind of geometry, one whose structural properties could evolve in response to internal content. In doing so, Riemann provided the conceptual and mathematical foundation for describing self-persistent geometric structures, stable configurations that could deform, interact, and evolve, all while preserving their essential internal relationships. Einstein would ultimately harness Riemann's insights to construct his general theory of relativity. The curvature of spacetime in Einstein's equations exhibits precisely the kind of geometric behavior Riemann had envisioned, gravity as a manifestation of the changing shape of the manifold itself. Riemann's geometry made it possible to speak mathematically about a world in which the very stage of physical events, the structure of space and time, was an active, lawful participant. Then came Einstein. While Newton's world was governed by coherent rules playing out on the stage of absolute space and time, Einstein proposed that space and time were part of a unified and dynamic manifold, spacetime. This manifold was not a passive container for events, but an active participant in the unfolding of reality. Energy and mass curved spacetime, and that curvature dictated the motion of bodies. Gravity was no longer a force acting at a distance, but the natural motion of bodies through the warped geometry of spacetime. Einstein's general theory of relativity redefined the structure of reality itself. Geometry was not the backdrop to physics, it was physics, and that geometry was a hyperbolic manifold. This brilliantly structured the rules, and the backdrop they played out on, into one coherent system. Reality for Einstein was not a set of fixed entities floating in a void, but a network of interwoven transformations. His universe was smooth, continuous, and lawful, where every change was a consequence of the structure of space-time itself, structure that must be revealed through principles that hold true for all observers everywhere. His equations showed that mass and energy are interchangeable, that light bends around stars, and that time dilates depending on speed and gravity. Just as Galileo measured patterns and Newton codified them into rules, Einstein showed that even those rules had deeper symmetries, transformations that preserved the structure of physics across all reference frames. Einstein's ontology was elegant and geometric, but it was also deeply epistemological. It told us not only what reality was like, but how our knowledge of it must conform to its constraints. No longer was the observer detached and unaffected. Instead, measurement itself became a kind of interaction with the structure of the universe. What Einstein offered was a framework in which the act of understanding was inseparable from the nature of what was being understood. Einstein didn't merely describe the universe. He showed that its structure was intelligible, lawful, and participatory. His work stands as a reminder that to understand the world is to belong more deeply to it. Then came Dirac. Just as Einstein revealed the large-scale hyperbolic structure of the universe, Dirac showed that the logic of its smallest structures could be captured in a single, elegant rule. In the early 20th century, Paul Dirac formulated the Dirac equation, a unitary, invertible, hyperbolic structure that wove together quantum mechanics and special relativity. This equation wasn't just a technical innovation, it marked the birth of modern field theory. It defined how particles, with mass and spin, behave in a relativistic world, and, more deeply, how the universe enforces the logic of persistence at the quantum level. His equation wasn't simply describing how particles behave, but revealing the logical scaffolding that made behavior possible at all. Where Newton gave us equations of motion and Einstein gave us the geometry of space-time, Dirac gave us the rule book that governs existence at its most elemental level, the balance of creation and annihilation, of presence and transformation, written in the language of symmetry. It was as if Dirac had stumbled upon the grammar of reality, compact, reversible, hyperbolic, a kind of syntax for how things persist through time. Dirac's worldview was one of extreme mathematical elegance. He believed that the laws of nature should not only be accurate, they should be beautiful. For Dirac, beauty in an equation was not ornamental, it was evidence of truth. He viewed the universe as a kind of hyperbolic harmony, where deep symmetries and unitary structures determined the logic of interaction. His ontology was one in which physical reality emerged as a necessary consequence of algebraic consistency and geometric invariance. To apply the Dirac equation to the real world, physicists must attach scaling parameters, fundamental constants that calibrate the abstract hyperbolic structure to empirical reality. These parameters, the speed of light, the reduced Planck constant, and the electron mass, allow the Dirac equation to faithfully describe the small-scale behavior observed in nature. Together, these constants anchor the structurally coherent logic of the Dirac equation into the world. In theoretical physics, it is common to simplify equations by setting its scaling factors all to 1. C equals h bar equals 1. This normalization highlights the essential form of the equation, reducing it to the bare rule set that defines invertible hyperbolic structures. Dirac was able to deduce the general symmetry constraints of being hyperbolically structured, but he didn't know which specific geometry was responsible for maintaining the universe itself. This means that he was able to determine the general form of the equation from consistency constraints, how it should look without its scaling factors, but had no way of deducing those scaling factors. Of all the aspects of the constants of nature, Dirac was especially fascinated with the fine structure constant, a dimensionless number that governs the strength of the electromagnetic interaction. Because it is dimensionless, it cannot be scaled away by renormalization. It represents pure geometry, just like pi. Dirac saw this mysterious constant as a keyhole into the architecture of the universe, a clue to the hidden structure of physical law. He famously once told a colleague who interrupted his focus with a speculative idea, "Does it explain the fine structure constant? Then come back when you have one that does." For Dirac, to understand the fine structure constant was to glimpse the geometric code of reality itself. The Dirac equation reveals the universe as a system governed by lawful transformations rooted in hyperbolic geometry. Without a way to deduce the scaling parameters that nature is using to fit itself to that balance, Dirac had no way to determine which hyperbolic space the real world conforms to, and neither did anyone else. But they did have a way to measure the constants of nature, the signatures of that specific hyperbolic space. After Riemann revealed the dynamic language of manifolds, and Einstein showed how gravity was the curvature of a hyperbolic manifold, and Dirac introduced the hyperbolic algebra of quantum persistence, we find ourselves poised to ask a deeper question. What is the simplest hyperbolic stage on which all of this can unfold? Then, Thurston entered the arena. If Dirac gave us the basic rules for persistent hyperbolic structures, William Thurston gave us the map of all possible hyperbolic worlds in which such rules could be embedded. In the late 20th century, Thurston revolutionized geometry and topology by classifying the possible three manifolds, the spaces that could act as full-stage arenas for persistent geometric form. His geometrization conjecture, now a theorem thanks to Perelman, showed that every three-manifold can be decomposed into pieces that admit one of 8 canonical geometries, of which the richest, most structurally expressive is hyperbolic geometry. Among these, the hyperbolic figure-8 knot complement stands out as the simplest, non-trivial hyperbolic three-manifold, compact, orientable, and complete. It defines the minimal structure that can persist within the logic of hyperbolic geometry, defining the simplest something that endures when everything else is flux. While Dirac revealed the rule set of persistence, Thurston showed us the stage where that persistence could most elegantly and logically live. When we describe the Dirac equation as hyperbolic, we are referencing the deeper geometric structure it encodes. The Dirac equation arises from taking the square root of the relativistic energy-momentum relation, which geometrically defines a mass shell, a double-sheeted hyperboloid embedded in Minkowski space. This surface, like the single-sheeted hyperboloid and the double cone, is a classic structure within hyperbolic geometry. In this sense, the Dirac equation describes dynamics constrained to a specific hyperbolic form. Dirac's work deepened a broader revelation about the relationship between symmetry and persistence, a revelation that was taken even further by mathematician Emmy Noether. In one of the most profound theorems in the history of science, Noether proved that every continuous symmetry of a physical system corresponds to a conserved quantity. Time symmetry gives us conservation of energy. Spatial symmetry yields conservation of momentum. Gauge symmetry gives rise to charge conservation. Noether's theorem formally grounded the intuition that what persists must do so through symmetry. Her work forms a conceptual bridge between the invariant structure Dirac uncovered and the measurable constants that define our universe. If Dirac gave us a rule for persistence, Noether showed that the presence of any rule at all is rooted in symmetry. To determine which hyperbolic manifold defines the substrate of physical reality, to unveil the geometry that obeys the logic of the Dirac equation, we must examine the footprints that reality has left behind, its etched-in internal symmetries, the constants of nature. Every constant of nature represents a conserved quantity, reflecting a built-in symmetry of the physical system.